This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions of software engineering topics at least once a month. SE Radio is brought to you by IEEE Software Magazine, online at computer.org/software.
This March 21st and 22nd, don't miss Tech Ignite in Burlingame, California, just minutes from the San Francisco airport. Come to Tech Ignite to get rock-solid info and forecasts on adaptive cybersecurity, emerging technologies, machine learning and deep learning, operational intelligence, and much more. Join tech superstars Steve Wozniak and Grady Booch, plus C-level leaders from Netflix, Google, IBM, Salesforce, GE Digital, and Intel to gain valuable insights and learn about real-world solutions you can start applying today. Register now for the IEEE Computer Society's premier conference, Tech Ignite, at techignite.computer.org and discover the truth behind technology.
For Software Engineering Radio, this is Robert Blumen. I have with me today Donny Nadolny. Donny is a Scala developer at PagerDuty working on improving the reliability of their back-end systems. He spends a large amount of time investigating problems experienced with distributed systems like Cassandra and Zookeeper. He runs the Failure Friday exercise at PagerDuty. Donny is a graduate from Waterloo University in economics. Donny, welcome to Software Engineering Radio.
Thank you very much for having me.
We will be talking today about debugging distributed systems. The idea for this show came from a blog post called Zookeeper's Poison Packet and a conference talk on the same subject, which I saw Donny give at the Velocity conference earlier in 2016. I wanted to talk about the bug itself and some lessons learned that can be applied to distributed systems problems in general. First thing, Donny, would you like to tell the listeners anything else about your background?
No, I think you've pretty much covered it.
Okay. Briefly, tell us what is PagerDuty's application that you were working on when this bug was discovered?
The core of PagerDuty's application is alerting people when their software has problems. So you generally have a lot of different monitoring systems. They all hook up into PagerDuty, and then our software will call or text or email your engineers to let them know when you have a problem. We also have a lot of other things on top of that to make it easier to coordinate these responses and to fix things quickly. At the time, I was working on a few different back-end systems in what we call the notification pipeline, which is the critical series of microservices that we have, which are necessary to take an event coming in from our customers, do some processing on it, and then actually make the notification, so call out to our customers.
I'm going to guess that because people depend on this system when their product is down, that it would be very important for your system not to have any unplanned failures or downtime. Is that correct?
Absolutely. We care a lot about having highly available software, and our goal is to be able to, we actually run our software across multiple data centers, and in fact across multiple providers, so not just AWS, also on Azure. And the goal is to be able to lose an entire data center while still remaining available.
Right. You talked about running on AWS. I'd like to introduce the concept of a region. What is a region in AWS?
A region is one of the units of fault tolerance that AWS gives you. So a region is made up of multiple availability zones, and an availability zone, you can think of it as a data center, although really an availability zone can be made up of multiple data centers, multiple buildings, but they're very, very close together. And within a region, different availability zones are also very close together. AWS has the goal of having each availability zone, which is within a region, each availability zone should be a unit of fault tolerance. So it should be nearly impossible for all of the availability zones in a region to go down although it has happened before. So internally in PagerDuty, we tend to think of a single region as a single data center. And so we spread out across multiple regions.
The point being then, these units of fault tolerance are things which can fail independently of each other, and you give yourself some redundancy by using more than one.
Yeah, that's right.
Okay. So in AWS, their regions are called things like US West 1, US East 1. Why would a system span multiple regions?
Well, the idea is that because a region can go down, even though it shouldn't go down, it should really only be an availability zone that goes down. A region can go down, and so by spreading across multiple regions, it means that if you have proper replication and things like that, you ought to be able to lose a region. And a region, when you're talking about US East 1, US West 1, that is a very tight geographic. That's a really tight grouping of buildings together. So if there were, for an example, an earthquake around there, even though you're in multiple availability zones, it's possible that it could damage all of those availability zones.
Sure, it could be something, even though AWS did a great job building their data centers out and the electricity and heating and cooling, it could be something totally out of their control, like a natural disaster.
Yep, and a good example of where even if you have lots of redundancy in your power or things like that, you have backup generators, you still have to have those machines be connected to other ones through your network. And you can have redundant paths for your network, but a natural disaster is the kind of thing that could take out all of your network connections to the rest of the internet or to other regions.
Sure. Are you aware whether Amazon routes across the public internet between regions, or if they have their own dedicated bandwidth that they lease?
I believe they have both. So I believe they do have peering agreements that can go across the public internet, but they do have their own fiber, at least for most regions, and I think for all, and that's what they use primarily. There's actually a case, I think about a year ago or so, that we experienced where there was a fiber cut, and the latency in one of the regions that we were in to some of the other ones, it went from being 20 milliseconds or so all the way up to being, I think, around 100 milliseconds, because I think the theory was that AWS was actually routing through their own fiber as much as they could, but it meant they were routing packets kind of partway around the world, even though the two places were really close, and if you went over the public internet, then the network connection would be fast. But because they were routing over their own internal network, maybe for cost reasons, the latency was quite high for several hours.
The problem we're going to be discussing, it originated in a component called Zookeeper. We did an entire show, number 229, on Zookeeper. I'd like you to briefly tell us what is Zookeeper and what is a Zookeeper cluster?
Sure. So Zookeeper is a distributed system which is useful for building other distributed systems. What it gives you is it exposes kind of a file system-like interface to you, except you don't store regular files in it. You store little bits of configuration information or coordination information. So you can do things like create a directory, create a file, atomically update a file. You can create a file where the name is guaranteed to be sequential if you have multiple concurrent clients that are trying to create the same file. You can also have a file that will go away when the client disconnects. Now, the idea with Zookeeper is that you then build on top of this small set of primitives to build other primitives of varying degrees of how high level they are. So you can use this to build distributed locking, where you want to make sure that only one node in the distributed system that you're building is a leader, for example, or it can take a lock on some entity or some set of entities. You can also use it, probably not recommended, but you could use it for service discovery, where you would create a file with information like your IP and your port, that's how to contact you, and all of your different clients would create that. And to do service discovery, to pick which node you want to contact, you just look in that directory and you pick one at random, and it will most likely be live because when it disconnects, shortly after that, the file would go away. At PagerDuty, we use it mostly for distributed locking, where we use it to protect different entities from concurrent modification. One of the reasons we do that is because we use Cassandra, and it doesn't really give real ACID transactions. They do have what they call lightweight transactions, but they're not quite as useful as you might think. So we use Zookeeper as a way to kind of gain some of the benefits of a transaction, at least some level of isolation from that. A Zookeeper cluster is how Zookeeper is highly available. When you run Zookeeper, you typically run it as in a cluster of 3 or 5 nodes. At PagerDuty, we typically use 5. And what Zookeeper does is it will first elect a leader, and then all write operations flow through the leader. That's how it can do things like give you sequentially named files when you try to create them concurrently. And the idea is that if the Zookeeper leader fails, one of the replicas can take over, because before it will have told the client that a write was performed, it will have replicated that to at least a majority of the Zookeeper nodes. So in that way, you can have the kind of the abstraction of Zookeeper be highly available, where any node can fail and you haven't lost any data.
Okay. I can see how that would be very useful in your business, because in order to ensure that your system is always delivering messages, you need to have a lot of redundancy, because pieces of the system might fail. But then when you have a lot of nodes that might all be trying to do the same thing or to cooperate in doing something, you want to ensure that everything that needs to be done gets done exactly once and not 0 times or 3 times.
Yeah, that's right.
Okay. Why does the Zookeeper cluster need to elect a leader?
In order to give some of the consistency guarantees that Zookeeper offers you, it's very, very helpful to have all of these operations go through a single node. That way it can do whatever coordination it needs on its own. So in Zookeeper, any write must go through the leader. So in order to have your cluster be available, it has to elect a leader first.
So I'd like to discuss a bug that you presented at Velocity. Let's start with, what was the first indication that something was not right?
The first indication that we had that there was a problem was actually with our regular application level monitoring that we had. What it had told us was that basically just things were becoming stale, work wasn't being done, and we ended up tracing that during the outage. We ended up tracing that to Zookeeper not being able to do any work.
So your monitoring was telling you that the system was stuck. How did you narrow down the problem to Zookeeper?
I believe what we had done in at least the first instance that we had of this happening in production was just through the logs. We were able to see that we were timing out when trying to talk to Zookeeper.
So you have a client, and it was trying to connect to Zookeeper, and it was timing out, either getting a connection or it requested Zookeeper to do some work, and that request timed out?
Yep, that's right. It was requesting Zookeeper to do some work, either reads or writes. Both of them were failing.
Sorry, the error manifested in production. Were you able to reproduce that in an isolated environment?
Until we were actually able to figure out what was going on, we couldn't reproduce it. So we did try quite a bit to reproduce it in our low testing environment, but we were never successful until the very end when we actually knew what was going on.
Okay, so what was the next step?
One quick thing I should probably mention is that one of the symptoms that we had seen was that even though Zookeeper wasn't able to do any work, all the processes were up. So it seemed like it should be able to, but it wasn't actually able to.
So the client was timing out. Probably the next thing you would want to look at is Zookeeper and see if there are any clues there. Am I right about that?
Yeah, that's right. So we we do have some good dashboards for Zookeeper. What they had showed us was that all of the Zookeeper processes were up. There was a leader for the cluster, but the cluster was completely hung. When we checked the networking between them, that was also fine, at least at the time that we checked. There was a network blip that had happened a little bit before, but when we checked, the network was completely healthy. The cluster was up, but for some reason, it wasn't actually able to do any work.
So when you say the cluster was hung, what exactly do you mean?
The processes were running, but if you tried to do a read or a write, then it would just time out.
Were there any error messages, log messages, health checks, anything that gave you more insight into why it got into that state?
So one of the annoying things about this was that the health checks that we were using, at least for Zookeeper, were all fine. So there's a very popular health check that a lot of people use for Zookeeper, which is you can connect on a certain port, you can issue it the 4-letter command, "Are you okay?" And it will reply back saying, "I'm okay," if it's up and if it thinks everything is good. Now, we did have monitoring on that. We had that command running regularly, but it actually showed that Zookeeper was reporting everything was okay. Now, we looked in the Zookeeper logs, and there were some kind of weird-looking things in the Zookeeper logs that we did try to investigate.
What's one of those, for example?
So one of them was this concept of Zookeeper trying to take a snapshot. Zookeeper, as I mentioned earlier, it gives you this abstraction of a file system. One thing I didn't mention was that you're meant to put in only really small configuration information or coordination information, and this is meant to fit in memory. So the entire database for Zookeeper is usually pretty small, just a few megs or maybe tens of megs, and it keeps a log of operations that you've done to it. Now what it does is every once in a while it will write out a complete snapshot of this in-memory database so that when you crash and recover, it can just read in the snapshot instead of having to replay a gigantic log of everything you've done since the beginning of time. Now, one of the early suspicious log entries that we had seen was this log entry saying that it was too busy to take a snapshot and that it was going to skip that snapshot. Now, when we looked into the code to see what that meant, it meant that it was actually in the process of writing out a snapshot when it tried to take a second one. Now, looking at the timeout of when it had taken the previous snapshot, several minutes had gone by before it was taking, or before it attempted to take the second one that it then skipped. So initially we thought that maybe there was some problem where that first snapshot was taking a really long time to write out and was then blocking this other one from happening, maybe because of, I don't know, some disk problems or things like that.
Okay, so you take it as far as you could with information that Zookeeper was already giving you. You didn't have a solution. What was the next step in your investigation?
Well, one of the things that we had tried was, so one of the key things that you want is obviously to be able to reproduce a bug. It makes it much, much easier to figure out what's going on if you can reproduce it at will, because then you can do this in your own kind of staging environment or low test environment, and then you can be a lot more aggressive at poking at Zookeeper or about enabling really verbose logging to let you know what's going on. So we struggled for quite a long time trying to be able to reproduce this. The closest that we had got was actually related to that log line of trying to take a snapshot. We ended up reproducing what would happen if there was a really slow disk. So a nice tool that we used for this was a tool called SSHFS, which lets you mount a remote directory of any machine that you have SSH access to. So we did that. We configured Zookeeper to put its files on that remotely mounted file system. And then you can use your normal network tools like IP tables or TC to mess with the network to make it be slow or to hang, and those things will manifest as disk problems by either the disk being slow or the disk hanging. Now, we had actually managed to get Zookeeper to hang in a similar fashion by slowing down the disk like that. Now, that seemed quite promising at first, but after we had investigated a bit more, we have other monitoring and other dashboards showing us disk metrics and things like that. And even though it seemed quite promising at first, we ended up concluding that that wasn't what was happening because our other monitoring showed us that really there wasn't any disk problems at the time. There were other log files that were being written out fine. And as I said earlier, this in-memory database, this snapshot that it was writing out was really small, so it would have to be really severe I/O problems for it to actually hang for as long as it seemed like it was hanging with this log line of it saying that it was skipping this snapshot many minutes after it had started the previous one.
You went down this path that turned out to be a dead end. Then you did have a breakthrough that enabled you to make significant progress. What was the big step forward that got you closer to what was going on?
So the way that we got that next step was by adding some extra monitoring to Zookeeper. So I had mentioned earlier that this "Are you okay?" health check showed that Zookeeper itself thought that it was healthy. What we had added was an external health check that was just simple. It would just do a write to a key in Zookeeper, and then it would try to read that one. Now, we added that health check, and the next time that this had happened in production, we managed to grab a stack trace from the leader at the time. And it was this stack trace, while the cluster was in this kind of up but stuck state, that let us figure out what was going on.
So you added this more intrusive health check. What was the thinking there of why that would be a useful check?
Well, what we had seen was that Zookeeper itself thought it was healthy, but the application wasn't actually able to make any progress by reading or writing to Zookeeper. Now, having a really general health check on the application, as close as you can to what the user would see, is very useful because it means that you can catch any problem, or pretty much any problem, even ones that you haven't even thought of, dependencies that you recently added, or anything like that. Because you have this health check of pretty much the customer or your user actually being able to do things. Now, the problem is that doesn't give you any information about which of your dependencies have problems or what's really going on. So that was part of the reasoning of wanting to add this second one. And it was also just the observation that our application wasn't able to read and write. So we wanted to have this extra independent check of whether or not something could read or write to Zookeeper, because it seemed pretty likely that Zookeeper did have a problem, but it could have been that our application itself was the one that had a bug that caused it to not be able to read or write to Zookeeper, and that Zookeeper itself was healthy the whole time.
I see. The built-in health check, you ask Zookeeper, "Are you okay?" It says, "Yeah, sure, I'm okay," but it might be lying to you, and maybe the only thing that it's able to do is say, "Yes, I'm okay," not able to perform its other functions that you have that you really need it to do.
Yep, that's right. When you look into the code, that "Are you okay?" check is really just a very tight mapping of it will take the command. As long as it can receive that command, it will reply with "I'm okay." It doesn't do any extra check itself to make sure that it's actually healthy. It's really not much more than just checking that the port is open and that Zookeeper has somewhat started up.
Okay, let's talk about the stack trace. What did you see?
What we had seen was one of the threads on the leader stuck trying to serialize a snapshot of the database to the follower. So Zookeeper runs as a cluster. You have the leader, you have all of the followers, and it, if you remember, it keeps this log of what operations you've performed. When a follower disconnects from the leader and then starts back up again, it has to catch up to where the leader is right now. So often it will just be able to grab the operations that happened recently, the Zookeeper leader stores them in memory, so it will just replay those operations to the follower. But if the follower is too far behind, then it has to send a full snapshot of the database to the follower. Now, this was where it seemed to get stuck. So it was a follower had disconnected, it had reconnected, it had requested a snapshot. The leader was sending a snapshot to the follower, but it was blocking when it was trying to write to that socket to the follower.
When you looked at the code that was indicated in the stack trace, did you get more insight into what was going wrong?
Yeah, well, the key problem here was that when it writes out that snapshot to a follower, it has to iterate over all of the items in this in-memory database. Now, when it does that, it enters a Java synchronized block for each item. Now, because it did that, and because it got stuck, that meant that this thread that was trying to write out the snapshot to the follower was holding on to a Java synchronized, holding on to a Java lock for one of those items. If you were to try to perform an operation on this item that had the lock taken on it, then of course you would block. Now, Zookeeper works by having a series of threads that process the requests that come in. They each do different things. So there's a thread that's responsible for writing out to the file system, to replicating it to followers, to actually performing the operation on the in-memory database. And these threads, or one of these threads, would then become stuck because it tried to take that lock that was being held by the thread that was writing out the snapshot. And this actually explained kind of one of the mysteries that we had seen before that I hadn't mentioned earlier, which is that sometimes the cluster would hang by having the leader just come to a dead stop. It would stop performing new operations, but sometimes the leader would actually fall behind the rest of the cluster, and operations would still happen for a little while, and then they would hang. And we ended up realizing that the reason this was happening was because depending on what kind of operation you try to perform on this item that was blocked by this other thread, you could hang near the end of this chain that does things after it was able to replicate that request to a follower, or you might hang right at the beginning of that chain before it was able to replicate a request to a follower.
Yeah. So I'm looking at this code right now of a synchronized block, then write to a network. That sounds like a dangerous coding practice, something that could definitely go wrong when you're holding locks on things and doing operations that have potential of lasting a long time.
Yeah, absolutely. So one problem here is that you're taking a lock on an item and then doing this operation that could, in this case, a network write, which could block for a long time. Now, one of the surprising things to me is how long this operation could block. So normally you think of a network write, sure, it could block for a little bit, but even if there was some, it would only kind of block until there was a connection problem, and then the socket would disconnect. But what we had seen was actually this problem lasting for well over 10 minutes, I think nearly 15 minutes in one case that we saw, of having the cluster in this state where it's blocked trying to do the write, and the TCP socket that you're trying to write to is just hung for that entire period of time.
When you found this problem in the code, the cause of the stack trace, and that was not the final step in debugging the problem.
No, it really just pointed us to more things that we needed to figure out to really understand what was going on here.
So after you found this stack trace, you identified where it was failing. What was the next problem that led you to?
Well, the next thing that we realized, once we knew that the code was blocking in this way, we could figure out why one of the followers wasn't taking over from the leader. Because the way that we resolved this when it happened was just by killing the leader. So restart the leader process, and then immediately one of the followers would take over and operations would continue as normal. But the thing is that you're not supposed to need to do that manually. Part of the benefit of Zookeeper being in a cluster and using a consensus algorithm, it can figure out, or it should be able to figure out automatically, that something is wrong and one of the other followers should be able to take over. Now, the way that it did this is by having the leader send a heartbeat to the followers. So every few seconds, I think it is, the leader will send a heartbeat to the followers, and the followers will keep track of how recently they've heard this heartbeat from the leader, and if it's been too long, then they kick off an election. Now, when we dug into the code a bit more, we realized why this wasn't happening, which was that this thread that sends out heartbeats to the leader, or this process of the leader sending out heartbeats to the followers, is actually done by a completely separate thread. So even though most of the important threads on Zookeeper are blocked or are unable to do any kind of work, you still have this one thread off on the side sending heartbeats to the followers saying, don't take over, essentially.
It sounds a little bit like the problem with the health check, where the system was doing just enough to pass certain checks, but not doing the things you needed it to do.
Yep, I think this is actually a pretty big problem in a lot of distributed systems. In any kind of leader-based system like this, you usually have some kind of timeout or heartbeat or things like that that are being sent. Now, the problem is that if this heartbeat or whatever it is you're sending, if you don't first check to make sure that you're actually able to make progress, then you can end up in this situation where the only thing that the leader is able to do is send out this message saying, I'm healthy, don't take over, even though all of the important things aren't able to happen.
From that point, what was the next stage in your investigation?
So the next step was digging into this TCP behavior to figure out why this TCP connection was stuck for so long. Now, we did have a little bit of network trouble before these outages happened, but when at the time that we would investigate, the network was actually healthy, but for some reason it was still blocked. The TCP connection was still stuck. Okay.
In my experience debugging, these type of transitions are very important, where you've decided we've extracted everything we can from this layer, the Java layer. The problem isn't there. We need to change where we're looking to another layer. How did you determine that the problem wasn't, or you weren't going to get any more progress out of looking at the Java and Zookeeper, and you had to go down to the network layer?
Well, it was really about trying to find a full explanation for what had happened. So even though we had gone through the code, we had figured out what was happening in Zookeeper, and in fact, by this point, we knew enough that we could fix it. And the fix is, at least that we implemented, was just not doing this network blocking right, not doing that within the synchronized block. Instead, in the synchronized block, you just take an in-memory copy of the thing that you want to write, and then outside of that block, perform the write. That way, even if it does get stuck, all of the important threads are still able to do what they need because you haven't blocked one of the objects that they're trying to take a lock on. So even though we had somewhat figured out what was going on there, we wanted to dig deeper to figure out why this TCP connection could be stuck for so long.
Yeah, and this illustrates another important lesson about this story. With an open source project, you can modify the code and deploy your own patched version of the project to test out bug fixes.
Yep, and in fact, we did run our own patched version for quite a while we were waiting for a new release of Zookeeper to be put out, which had incorporated our patch.
Yeah, I'm going on a bit of a tangent away from the investigation. How did the Zookeeper community respond? Did you get any inspiration from the community and were you in communication with them around this issue?
We had opened up a ticket on their ticket tracker describing what this problem was that we had seen, And actually, we didn't even open that up until we had a fix for it that we had tried out. And once we had that, they were very receptive and quite happy to incorporate it into the project.
Going back to the investigation, then you determined that the TCP behavior was not well understood. How did you proceed with your investigation from that point?
Well, the big thing that didn't make sense was a connection on the leader being in the established state and blocking this blocking write coming from Java, staying there and being blocked while this connection was established. And yet on the follower side, it didn't know about this connection at all. It had already forgotten about it or something like that. And yet it was still established, and we had seen this staying in this state for many minutes.
Yeah, so TCP, it's a state machine, and the two ends should ideally agree on what the state of the connection is, or they should reach an agreement fairly quickly. Is that correct?
Yep, under normal circumstances, they should.
What was going on then?
We decided to look into what happens to TCP connections under packet loss or under network isolation. So one of the things that we started experimenting with was establishing a connection and then introducing a network partition so that these two sides of the TCP connection can't talk to each other, and then having one of the sides kind of playing the role of the leader do a write and watch what happens with retries, watch what happens to the connection state, when does it get terminated, how long does it take, those kinds of things.
So what kind of tools did you use to examine this?
What's very helpful for this is using TCP dump, which will capture all of the packets that are being sent, and then copying that over to your machine and opening it up in Wireshark to take a look, as well as using Netstat regularly to look at the state of the connection. And of course, IP tables to block packets.
Did this issue have something to do with the cluster having members in different data centers and having to go across a much longer network path than within a single LAN?
To an extent, yes. These kinds of problems can happen when you're running just within one data center, but they're much more likely to happen when you're running across multiple data centers. And in this case, it was going over the public internet because these were two data centers that were being run by different hosting providers. So even though these things can happen in kind of a local network or in one data center, a lot of these problems are much more likely, or they can persist for a lot longer. You can have much higher packet loss lasting for a lot longer when you're running over a wide area network.
Are you aware in the distributed systems field generally, do a lot of bugs tend to surface when people build these bigger clusters that span across the public internet?
Well, I think even now it's still fairly rare to run these systems across multiple data centers across the public internet, separated by real wide area network latency rather than just really small amounts. So with Cassandra in particular, there are some people who are doing that, although their setup is usually a little bit different from ours. They're doing more of an asynchronous replication between their data centers, doing writes with a consistency level of what they call local quorum, meaning you only care about the consistency within one data center, and then that will be asynchronously replicated across to another one. In our Cassandra clusters, we use the regular quorum consistency, which will synchronously replicate across a different data center. And in Zookeeper, it's basically always like that. It will always be running at kind of the equivalent of what Cassandra would call quorum consistency, where you always write to the majority. So if your nodes are across a wide area network, then you will always be writing across a network.
So in your presentation, there's about 15 slides dealing with the TCP protocol. Could you condense down what you eventually found to be the cause of these long timeouts?
Sure. The kind of root problem with what we were seeing was you can have a follower and a leader. They establish a TCP connection. If you introduce a network partition between them, so they aren't allowed to communicate, and you try to write on the leader, it will try to send this packet to the follower, and it will wait to hear an acknowledgement back. If it doesn't hear that acknowledgement back, it will keep on retrying, increasing the delay between subsequent attempts of retrying to send this packet. And that actually gets up to be quite a high delay in these retries. So the maximum, which is hard-coded in the kernel, is it will wait 120 seconds between retrying, and it's doing a doubling behavior of each retry that it does. And it will wait for many, many retries, 15 retries. And so when you put all that together, when you try to do a write, and there's a network partition, that write could block for at least 15 minutes, and it could be higher depending on some other parameters and kind of the initial network latency that was going on.
Then you say hard-coded. Was this something you could fix by tuning some of the kernel parameters about TCP behavior?
You could kind of work around this indirectly, but the only tunable parameter that would affect this is the number of retries that you allow TCP to do when it doesn't hear back this acknowledgement. So if you lowered that, then you would indirectly get kind of a lower, you could think of it as a timeout on when you were doing a write, but it's an indirect way, and it's kind of not really ideal, because then if you do have packet loss, you would get fewer retries before it would just give up. I have been intending to make some of these parameters a bit more configurable, because what I would like to have is keep the number of retries the same, or even increase the number of retries, but cap that maximum retry timeout at some configurable parameter so that you could set it to be quite a bit less than 120 seconds.
Yeah, that's pretty long. There's one other slide I found quite interesting. It talks about IP tables and Netstat. Now, those are two tools in the Linux world that there's a lot of Linux tools, and they're not all distinct. There's a lot of overlap between what they do. The interesting point on this slide, it says IP tables connections not equal to Netstat connections. Explain what that means.
I'd mentioned earlier how when you try to do this right, if you have a full network partition between these two sides, then you could have that write be blocked for 15 minutes or more. But that wasn't quite what we were seeing, because when we went to investigate the network health, we saw that the network was actually healthy, but the connection was still stuck. So to figure out why that was happening, what we ended up seeing was that the follower side, or one of the sides of the connection that wasn't trying to do this right, would disconnect. It would try to close this TCP connection, but there was still a network partition, so it wouldn't be able to send this FIN packet, it trying to tell the other side that it wanted to close the connection.
Right.
It wouldn't be able... Oh, sorry?
Yeah, so the FIN packet, that's part of the TCP state machine where the two sides are trying to agree to close the connection.
Yep, that's right.
Yeah,
so
okay.
It's trying to close the connection, but if you have a network partition, obviously that's not going to get to the other side. But you don't want to have this state kind of this connection that you're trying to close remain there indefinitely. So after a certain amount of time, you just consider the connection closed, even though you haven't been able to talk to the other side. Now, we were running IP tables as a firewall to only allow certain connections through, only connections on certain ports, or established connections that you knew about. Now, this follower side, what would happen is it would close the connection, or it would make the attempt to close the connection. It wouldn't be able to tell the other side, but it would eventually mark it as closed. But now, the network can heal, and one of those retries from the other side that's waiting this 15-minute time, one of those could come through, but IP tables would then block this packet because it didn't know about that connection. And so in this way, you can have these two sides where one of them considers the connection established, one of them considers it closed, and even though the retries are coming in, that one side is blocking those packets, and so you never get this other TCP packet that would come through, a reset packet, which is normally what would happen when you try to talk to a machine that didn't know about the connection. But because IP tables was blocking it, it would never get through, and so the network can heal, but you still have this connection stuck. Now, to get to the point about these IP tables connections are not equal to Netstat connections, what I hadn't realized was that IP tables has its own state machine that it uses completely separate from the regular kernel state machine. So you can, and in fact, the IP table side just uses simple timers that are different than the knowledge of the kernel of whatever retries it has and exponential backoff and things like that. IP tables just has simple timers that it uses based on watching packets come in and out. And it turns out that that timer, at least with the default behavior, it can actually consider a connection be closed after one side attempts to close it earlier than the regular TCP kernel view of that connection. So you can, in fact, have, if you do this setup of having a network partition, have one side try to write, have the other side try to close it, wait for a little while, you can be watching Netstat and see the connection still be there in the, I think it would be the fin wait connection, or I forget which TCP state it would be in, while you're waiting for it to be closed. You could see that in Netstat, but IP tables might have already forgotten about the connection. And so if the network had healed right then, you could have packets come in, you could see on that other side it still knows about the connection, but IP tables would drop it, and so you would still not get that reset packet going back.
So the reason I found that interesting when I was thinking about the outline for the show, one of the points I'd written down on lessons learned was that these tools we rely on lie, or maybe that's overstated, but it's definitely a theme in your discussion that you have these health checks and heartbeats and tools, and they tell you one thing, but you can't always take it at face value. It doesn't necessarily mean exactly what you might think it means.
I think one of the things that made this problem difficult to investigate, but also really interesting to investigate, is when you have to go really deep, go beyond the regular layers that you're looking at. In this case, digging really deep into what happens with TCP behavior under network isolation. And yeah, really kind of understanding, or in my case, learning a lot of these different tools to figure out what the real state is. I spent quite a lot of time playing around with a few machines, introducing network isolation, and then watching what actually happened to the TCP state and to the retries that were going on. And I actually ended up seeing kind of some maybe undocumented behavior, or maybe a bug in the TCP kernel stack, where you end up getting one extra retry than you would think.
Are we still learning more about TCP and how it behaves in edge cases?
Well, I think a lot of people, if you're never forced to go digging into it, you kind of take it for granted that you establish a TCP connection, you write stuff over it, and everything is fine. If things go wrong, then it gets disconnected. It's kind of these weird edge cases that come up that can really throw off your understanding or force you to dig into what's going on there.
So there's one more layer in the debugging about IPsec, and I'm going to skip that, but people who are interested should look at your slide share, and we'll link to that in the show notes. I want to get more into lessons learned that the rest of us can apply in debugging problems that we have. What is a key lesson that you learned as an engineer from investigating this problem?
I think the biggest one that I learned is not really a technical thing, but it's more that you need to be really persistent. So when we were debugging this problem, there were several days in a row where I came into work and the entire day I spent looking at logs, going through Zookeeper code, and basically not making any progress. I was making some progress in terms of gaining an understanding of Zookeeper and of TCP behavior and other things like that. But in terms of making real tangible progress to figure out what was going on, it was just no progress at all. So I'm very glad that we were persistent in this investigation to figure out what was really going on.
I've had the experience debugging, and I don't have this experience writing code, but I've had this with bug chasing where I start to despair and I think I am never going to find this. It's just too hard. Did you ever experience despair or the feeling, the thinking, I'm just going to give up? Or did you always have optimism that you would find the root cause?
Well, I wouldn't say that I had optimism the whole time, but I never really had that kind of despair. It was a little discouraging to go for so long and to not make any progress in terms of kind of the Boolean measure of have I figured it out or not. But luckily, I never really ran out of ideas of what to try next. I had lots of ideas of things that it could be, or kind of the next step of something new that I should investigate, or some new bit of the code that I should look at, or things like that.
You gave this presentation about the problem, the full investigation. Were you the sole person working on it, or were there multiple people?
Nope, there were multiple people. So I think I was the one who investigated for the longest, but I had a couple of my coworkers who were kind of on and off this investigation, and also some others who I asked about networking behavior who kind of gave me some pointers of where to investigate next.
The problem, as you chased it around, it was from Java to the Linux kernel to the TCP protocol. Often people will not have a really deep knowledge of all those layers. Did you collaborate with people who were expert each at a different layer? Or how did that work?
Well, I'm fairly experienced in Java, so I didn't have too much trouble going through the code base for the Zookeeper code, which is written in Java. It was really the networking behavior that I needed a tip from one of my colleagues, Evan, who was kind of gave me that tip about TCP being able to, or really paying attention to the state that the connection is in, particularly under network isolation.
You have a number of lessons learned. What is another key lesson you learned from this process?
One of the interesting things that I thought about during this was how interfaces or abstract methods can make it a bit harder to be confident that your code is correct. So with this call in Zookeeper that was taking a lock and then performing this potentially blocking operation, this TCP call, which, as we learned, can block for quite a bit longer than you might expect. I had thought about how the call that it was performing that ended up writing over the socket was actually an interface method. So with that, even though I don't think it was a factor in this specific one, it's easy to imagine a situation where you're writing code, where you take a lock, and then you call out to an interface or some abstract method, and at the time you write that code, all of the implementations of that are non-blocking. They all operate just in memory, they're guaranteed to finish in a certain amount of time, but it's possible for somebody later on to add a new implementation of that, which would all of a sudden make your existing code incorrect. And again, as I said, I don't think that came into play here, but it was just kind of an interesting thing that I noticed, that it can make this kind of analysis or this kind of problem a bit easier to occur than you might think.
Yeah, I have seen some critiques of object-oriented programming that raise this point that by creating abstract methods and interfaces, you can't guarantee that all the implementations that people will plug in will honor all of the contracts that are assumed by the frameworks or higher levels of the stack that call them. And I think this illustrates that point. I want to summarize in some of the lessons we talked about earlier were about monitoring and health checks. What did you learn about that?
So I think even more strongly now than I did before, that it's really good to have high level health checks of your application to make sure that you can catch all these different things, but also that it's very useful to have kind of these narrow but still end-to-end tests of dependencies that you have. It then makes it very easy when you get paged and you see, instead of just getting a message saying that, there's some problem in the application, it's good to get that rather than nothing. But it's also nice to have either another alert or a dashboard that shows you, and here's the one dependency that is messing up.
Right. So you want computers to do as much work as they can in collecting useful information about the problem before you start working on it.
Yeah.
Okay. Yeah. And what about health checks?
Health checks are another thing that I think could be improved in a lot of systems. So it's very easy to make kind of a naive health check that just replies and says that you're healthy as long as the process is up. But you can have this problem where that's then the only thing that is healthy. So I think it's also important to tie in more of a deep health check whenever you're doing that kind of thing. Don't just reply right away saying that it's good. Either perform an actual operation as your health check or something along those lines. And I think that this is important for one part, for monitoring the dependencies of this is a great way of checking your dependency. Perform a simple operation, and that's their measurement of whether your dependency is healthy. But it's also useful in any kind of leader-follower based system where the leader is preventing followers from taking over, to do some kind of deeper health check locally to make sure that when you're getting requests, you are actually able to process them. And it's only then, if you know that to be true, that you would then send out this message to your followers saying, don't take over, everything is good.
Sure. This reminds me of a retail system I worked on. We use an external monitoring service called Pingdom that checks that your servers respond to HTTP. We also implemented check that would log into the site, create a customer, buy a product, put it in the cart, and check out or cancel the charge at the last second. Because if you can respond to HTTP but you can't allow people to buy products, then something's not right.
Yep, absolutely. That's a great thing to do. You can pick kind of whatever your most important feature is. In the case of a shopping site, can you go and actually add and buy a product? And that's a great health check to use. So PagerDuty also has a similar system we call Watchdog that performs end-to-end testing against our system, where it acts as a customer would by sending events to our regular public endpoint, using our public API to perform various operations that we think are important, and then making sure that it actually gets delivered in the end. And that's a system that we run against production, but because it's kind of outside of our regular system and only uses our public endpoints, you can even point that at any of our different environments and use that to check that, for example, the load test or different staging environments are healthy as well.
Yeah. And now there's one more lesson which I learned from your experience and also from reading the blog post about the Zookeeper's poison packet, which describes a different but similar bug. And I'm not sure if you learned this lesson because I think maybe you already knew it and so you didn't need to learn it. But I come from a software development background, and the mindset is there's a bug in my code. So I'm going to look in my code and find where the problem is. And I'm just going to keep looking in my code until I find it. Or maybe the libraries, if they're open source and they're in the same language or same stack. I made a transition in my current job to DevOps, where one of the big shifts is we're looking at a lot more layers of the stack. A lot of the issues I deal with is any possible layer could fail, sometimes multiple at once, and just opened up my mind a lot more to all the different places that things could fail and that I can't come into issue with too much of a preconceived idea about where the failure is. So that isn't really a question, but you can comment on that if you like, or we can go to the next question.
It certainly makes it harder to figure out what's going on when you can't just assume that it's your code that's wrong, when you have to go into these other layers or other systems that maybe had guarantees, or maybe you thought they had certain guarantees, but it turns out that they don't. It makes it quite a bit harder to debug for sure.
So this will be my final question, Donny. In reading the blog post about Zookeeper's poison packet, which has a lot in common with the issue we've been discussing today, the problems were not the result of one single bug in one behavior. It was interaction of multiple bugs, or not even bugs, but behaviors that were not well understood that interacted with each other to produce the final problem. Do you have any thoughts? Why is it that we get these type of multiple failures? Why isn't it just one thing?
Well, in security, they have the concept of defense in depth, where you want to have multiple layers of protection. And in a way, in a lot of distributed systems, you often get that. When you have this replication, usually you can just suffer the failure of a node and you're fine. These problems come up.
My question, is this because at the level you're building a system like this, you have a wealth of best practices and knowledge? You know how to plan for, okay, a node fails. Okay, the cluster loses a member. The easy cases, you've thought of them. And that leaves the hard cases.
Yeah, I think in a lot of ways it's when your assumptions are violated that then you start to have problems like these. So in this Zookeeper problem that we've talked about today, the assumption that was probably made that TCP won't block for that long. So even though it might take a variety of failures or some weird network conditions to expose this, most of the time it wouldn't happen, but there is this case when it can happen. And that assumption being violated then means that you can have this bug. In the poison packet example, it was not just assumption, but supposed to be a guarantee that TCP won't corrupt your data. It has checksums that are supposed to prevent that. But in the kind of multiple cascading problems or multiple combined problems, we did end up having TCP data be corrupted. And then the bad part there was that the failure mode of Zookeeper, when that happened, ended up being in this stuck state rather than being able to cleanly crash and let another node take over. I think this is another tough problem to deal with. It's when you have a node in this sort of degraded state where it's not completely healthy, but it's healthy enough to kind of occasionally send out heartbeats, or healthy enough to start taking requests, but not healthy enough to finish them in a reasonable amount of time.
That makes me think about how, as programmers, we're trained to think in layers. If I'm implementing Zookeeper deals with a network, that's another layer. So I'm going to make some assumptions about that layer as a programmer, and if I don't have in-depth knowledge of TCP, I'm going to probably make maybe a little more optimistic or best case assumptions about the network, which are okay as long as they're true, but then sometimes they're not.
Yep, having these different layers, having it be well encapsulated like that, it means that you can be a lot more productive because you now don't have to worry about kind of data being ordered within TCP or about corruption or anything like that. You just use this nice abstraction, which makes it a lot easier for you to build a system. But then when your assumptions are violated, you can have problems. One interesting one that I thought of a while ago is that you have this guarantee in TCP that data is ordered. So when you write it, even if the individual packets are delivered out of order, TCP will reconstruct them and give them to you in the right order. Now, the kind of really edge case that I thought of is that what happens when you then disconnect, or if you have some amount of packet loss. Usually what your client or what your system will do is it will establish a new TCP connection. Now, the ordering of data between those two connections isn't guaranteed at all because they're different connections. And you can think of maybe a pathological case where one side will have written some data that will have been, it will suffer packet loss and it will be retried. And in that time, you go and you establish a new connection and you write some new data. But now this thing that you sent second will actually come first. And the other side might even get that data that you sent initially later on. And that could cause problems. So even though you have this abstraction of TCP is ordered, you potentially could have this weird edge case of, well, maybe it's not.
Yeah, it does exactly illustrate that. Now, a minute ago I said it was going to be my last question, but I thought of one more. In the programming job market, the emphasis, it's very focused on what skills people have. People will list their Java programmer, Python, Linux on their resume. Do you think that debugging is a distinct skill set that can differentiate you and make you more valuable to a company?
Well, it's an interesting question. So I certainly think that debugging skills make you more valuable and that they're extremely useful. I don't know whether I can say for sure that it's a distinct skill. I think maybe it is, but I'm not quite sure.
Okay, wrapping up, we have talked about the Zookeeper blog, SlideShare. Are there any other resources or anything you personally post that you would like people to have a look at?
Well, I keep a pretty low profile online, so I don't have too much to share from that. One thing I would like to pitch, though, is this the concept of doing fault injection, or we call it Failure Friday. Netflix has coined the term chaos engineering. I think that's a very useful thing to do to distributed systems and to any system to make sure that it's actually correct.
Yeah, that would be a great idea for a show, so maybe we'll do a future show on that.
Sounds good.
Yeah, Donny, thank you very much for speaking to Software Engineering Radio.
Thank you very much for having me on the podcast.
For Software Engineering Radio, this has been Robert Blumen. You can reach us by email, team@se-radio.net. Find our group on Facebook or LinkedIn, and on Twitter @SERadio. Thank you for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more information about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can write comments on each episode on the website or write a review on iTunes. Mention or message us on Twitter @SERadio, or search for the Software Engineering Radio group on LinkedIn, Google+, or Facebook. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under the Creative Commons 2.5 license. Thanks again for your support.